Hey guys, welcome back. It is a lazy Monday afternoon at the time of recording. I've had a pretty intense weekend with a lot of stuff to do and haven't exactly decided what to work on this week. I have a few options, but in the meantime, I think we're going to do a little bit of C++ to SIG porting today, just as a laid-back little exercise in porting some gameplay features over to SIG. And I've had a post-it note on my monitor for a while now to port over the tire track rendering system from slide to means. So basically from my old game project written completely in C++ to the new one, which is still using the same C++ engine, but where the gameplay code is written in SIG. And so if we go to the Madrigal Games website and look here at the blog, I actually wrote a small blog post. This was already about 2 years ago. So here we have some screenshots from Project Slide about tire tracks and how I implemented the system for that game. And you can see some examples here of what the tire tracks might look like. Basically, we have two different types of tire tracks. We have the dynamic ones that are left behind by vehicles driving around, such as this. And then you have the static ones that you can actually, as a designer, you can place in the level editor. They both use the same kind of rendering system that is part of the basis game engine itself. It's pretty much designed with Project Slide in mind. So it is very much geared for exactly this kind of thing. It's not super flexible, but it's kind of easy to use. Basically how I do it is that I generate this kind of mesh that you can see. This is a debug view. Actually several meshes, because if you have some airtime, like you can see here, for example, the track sort of is ended and another one begins where you land. And then this mesh is then rendered to a texture which is then applied to the terrain finally. And you can see here that at this place it gets a little bit red, and that means that there's more slipping, and it can kind of fade in and out between two textures, one where you have perfect grip and one where there is complete slipping, and then it can fade in and out between those two. And you get tire tracks that look something like this. And so the post-it note that I've had on my monitor for a while now is essentially about posting or porting the C++ code which controls this stuff over to SIG so that we can use it from the SIG vehicles in means. And in this video we're gonna tackle the dynamic ones, so that when you're driving here inside means, driving around on the terrain, you get nice tire tracks left behind by the vehicle. And then I'll probably do the static ones later. They should be reasonably fast to do. Maybe not that interesting once we've done the dynamic ones. I think this should be a pretty easy and reasonably small thing to do. We can do it just in one video. So let's have a look at what we're dealing with. Basically we're talking about a single component in C++. So tire track component looks something like this. It's quite small, and we will just simply port this over to Zig and then add it to one of the vehicles and make sure that it works. So, should be pretty nice. Nice and easy to do in one video. Right, so I'm gonna bring this over to the left side here, my left monitor, which I am not recording, but which I can use as a reference when creating this component. So I'm gonna go to means, add a new file, and call this tire track component.zig. And we have a snippet here for a new component, and we can just call this the same thing, tire track component. And for the registration name, so I need to click somewhere to get rid of the multi-editing. I'm just going to add means dot here so that the registered name of this component will be means.timeTrackComponent. And this component actually will have some blueprint properties, which means that we'll probably want to actually register this with the asset browser in the Basis engine to get a nice UI when we actually add this to the component. So basically what I'm talking about is here in the asset browser we have the blueprints, gameplay blueprint. And most of these components that you see here, they show this message that the UI definition is missing for this component. And that means that we can't really set any settings on the components themselves. We can just set the name and the creation policy, basically where we want it to be created. But components can have all kinds of properties. Like here we have the mesh component, for example, and it has all of this stuff here that you can set. So for the tire track component, we will want to be able to set the type, and we will want to be able to set the width of the tire. So basically how wide the tracks should be. And in here we have something that I've pretty much just copy-pasted from the project slide from the previous game projects. And you can see that it's a texture. It's called tiretrackpatterns.png. And we have a few of these patterns. We have essentially like the perfectly gripped one, the one where the wheels have perfect grip, which is this strip here, and then next to it we have the one with where there's no grip, so there's complete slipping. And you can see that we have three types of patterns here, and the slipping version is just using the same. So the type of tire tracks, that's just a number that we will need to specify, and it's essentially just an index into this texture. So this first pattern here, as well as the slipped version next to it, that is tire track type 0. Then we have 1 and 2, etc., and we can add more of them here later. And this tire track patterns texture is already loaded, or it should already be loaded by the means game project. So shouldn't really have to do anything to get this loaded. It's kind of part of the base project currently, and you actually have to modify the engine source code if we don't want to actually load that currently. Right, so what we need to do here is there's something called tire track renderer, which I have already brought over to Zig, as you can see. It's a pointer, so PTR. It's a pointer to something that lives in the C++ engine. And we have dynamic tracks and we have static tracks. And the way we actually use this system is that we register a tire. So for the scout vehicle that we're using in lots of these videos, we're going to have 4 tires. So call this 4 times. We get a tire ID back, which you can see here is really just an alias for an unsigned int of 32 bits. When we're done with the tire, we will unregister it, and as long as we have the tire registered, we can begin a tire track and we can end a tire track. And then while the tire track is begun, is active, we will update the tire track with information about where the tire is actually in the world. So we have a contact position, movement direction, longitudinal slip, lateral slip, and ground normal. So longitudinal slip is essentially like slipping along the axis of the tire, and then lateral slip is essentially like slipping during cornering, things like that. So both of them can go between, I think it was 0 to 1. And then the system sort of nicely blends all of this information together to render the tire track texture. And then, depending on where you are actually looking in the world, it renders them to the terrain. So the system is limited in the sense that you can't actually draw tire tracks with this currently on top of meshes. You would need to have like a special material for that. So it's currently it's limited to terrains only, but we can perhaps make it more flexible in the future. But this is essentially the API that we will want to have, the API that we will want to use from our new component. We have the tire track component here, and we can just add it here to the components. So we can do tire track component, and we will import tire track component, and it should already have the type for us there. And we will add it here to this list, and this list then gets fed to the engine. And that is the only thing we need to do to add a new component to our game. Let's just make sure that it builds at this point. And right, so what's the next thing we need to do? I'm going to look here at my C++ version that I have on the other screen, and I see here that we don't need an update method, so we can just remove that. We do need a tick method, so that's where we will actually update the tire track. And we probably don't need to receive any messages in this component, so we can remove on message received as well. And I think that's probably what we will want to have. All right. So the first thing that we'll want to add here is a small helper struct for ourselves. So let's do const tire state data. That's a struct. And this thing will have a few things. We'll have a boolean, whether or not it's touching the terrain currently. That's a bool. It will have the tire ID. So here is where we will start bringing these things in. Let's do tire ID. First of all, that would be basis, renderer, tire track renderer, and tire ID. So that's the ID of the tire, renderer ID, tire ID. And then we will need the state info of the tire. So this is the information that comes from the physics engine. So we'll call this, I think it's the vehicle wheel state info, I think is the type. Let's have a look and see if we can actually find it here. Yes, vehicle wheel state info. So this guy contains a bunch of information about the wheel on the physics engine side of things. Here's, for example, where we can read the longitudinal slip and the lateral slip for the wheel at a certain point in time. So that's important information that we will want to have. We will also need to have the vehicle controller, because that is where we can actually get that information. So I think we actually, in a previous video, we looked at this vehicle FX component, and this is where we, for example, we play the sound event for the engine. So this guy already has a bunch of types here declared for us. We have a vehicle controller component, and out of the vehicle controller component we can get the vehicle controller pointer. So let's get these guys. I'm gonna bring this to the side here, and we can just bring these guys in. Right, VHL is vehicle helper library. We need to import that to be able to use its types, so that's good. All right. Then, what is the next thing that we'll want? Probably we'll need this vehicle controller as a member here, so that we can read its stuff. And this guy is actually gotten here in onObjectCreated. So onObjectCreated is called when the game object that this belongs to, so the vehicle essentially, is fully created. All of the components are created at this point. So here we get the game object, we get the component of type vehicle controller component, and we assert here, just straight up give you an error if the vehicle controller component is not found, because this will be a mistake essentially. And then we can get the control component out of that, and we set the pointer to the vehicle controller here in our member. And you can see that this is also a pointer. This is a PTR, so if we go look at this, it basically just has an int pointer here. So it's not a pointer in the sense that you know, this thing here is. You can see the type here, even though I can select this part of this helper text, the type text that Visual Studio gives me, but you can see that it has like a question mark asterisk, so it's an optional pointer to a component. That's an actual pointer. The pointerness of the vehicle controller pointer here, the PTR stuff, this is sort of baked into the type itself. This represents a pointer to something that lives on the C++ side. Sort of like a convention that I use here for the basis game engine. Anything that ends with PTR is really just a wrapper for something on the C++ side. Alright, so now we have the vehicle controller. We should be able to read stuff out of this, and we can do it like this. So get state info, but we'll get back to that in a little bit. What we'll want to add here to this is state info. I can type info apparently, and it is of type vehicle wheel state info. Right, so we'll keep a list of these guys around, and that should be fine. Right, I think I had something like, is it vehicles.zig? Yes. This has a max wheel count of 8. That is how many wheels a vehicle can currently have in basis. So we should be able to just add that that array there. And I think typically I have my sort of declarations up front, and then I have fields here. Take one of these horizontal lines away. So just looking at what we have here in the C++ version, I'll put it on the screen for a little bit. So here's the helper struct that we had. We have the blueprint properties, which will give us the track type and the width, tire track type and tire track width. We have the transform component. Let's see what we actually do with this guy. I haven't rehearsed this at all, so what do? Yeah, we get the linear velocity out of the transform component. All right. We get the world matrix out of it. Okay, we just simply calculate the movement direction of the tire. Okay, that's fine. We do it sort of stupidly here in the update, or the tick function rather. We have a loop. We calculate it for every wheel here, even though we don't really need to, because the movement direction will be the same for all the wheels. So let's be a bit more smart about this in the Zig version. But yes, you can see here that the component, which essentially starts here, after just setting everything up, almost everything is here in this tick function. And the tick function basically checks the information. So we get the wheel state info. We do a bit of ray casting downwards to see if the wheel is hitting the terrain or not. We can get information about whether or not the wheel is standing on something from the physics engine, but I don't think we can get the information whether or not it's standing on specifically terrain. So I think that's why this thing actually does a ray cast downwards to determine that. And then we basically check here if it didn't touch the terrain, but it is currently. Then we have like a touchdown. Now it is actually touching the terrain, so we begin a tire track here and we update it. If it is still touching, then we simply update it. And if it's no longer touching it, then we end it. And this else is kind of pointless here, but it's of course executed if it was in the air and it is still in the air. Right, and then we just assign the new state here to the helper struct. And that's kind of the meat of the whole function. So not that tricky. But we'll see if I run into some issues actually porting this to Zig, because occasionally I run into something where I just kind of have to read the Zig manual because I'm not that experienced with Zig yet, so we'll see how it goes. But cool. Right, so we do essentially the same thing we did on the Zig side already. We get the transform component. That's not really anything we have to do on Zig. There's a transform API that we can get without getting the transform component. But we get the vehicle controller component and the controller out of it. And then we get a render scene. And from the render scene, we get the tire track renderer. That's the API to this whole system that we're going to use. We get the wheel count, and then we initialize these wheels by calling a register or tires. Wheel and tire can be used almost interchangeably here. So register tire with the given track width. This is basically like, is it a right side tire, as you can see there from the list of components, and then the track, so the track type, which is the index into the texture that we were looking at later. So that's cool. I wonder why I set this contact point to like a really big number. I'm sure there was probably some reason for that. Yeah, it's been a few years since I actually wrote this, so I don't remember everything. But let's see. So invalid tire renderer IDs, okay. Yeah, we just mark it with this value if we don't actually have a tire for that index. Okay, cool. Let's try to get this brought over into Zig. Shouldn't be that tricky. So basically we have a list of these helper structs, and we call it tire state datas, like this. And the number of, actually it would be like this. The number of these guys is then basis, physics, vehicles, and max wheel count, which you can see there is 8. We looked at this just a second ago. Tire state data. And do I need to actually initialize that array somehow? I don't know. Do I do that somehow with something? Typically, I think I've just initialized them to 0, but yeah, I'm not sure. I guess we can do that. We can just initialize these to 0. They will be initialized before we actually start using them anyway. So let's do that, and then we'll have another member here called mTire count for actually holding the number of tires that are active. But I wonder if we should use a slightly nicer member for this thing, because there's something called, let's see, we can do something like const tire state data list, and we have something called std, is it bounded array? Yes. And tire state data, and here we simply give the number of maximum, the upper bound of this list, so max wheel count, like this. This might be nicer. So now we can then just do tire state datas, and it's like this, right? So one of those guys, and we need to start tire state datas. Come on, and we initialize it and just give it 0 like this, right? And do we actually need to, yeah, stupidly we need to actually call try on this, even though we initialized it to 0, so there should never be any problem actually doing that, but that's how it works. And this is essentially like almost like an std vector in C++, even though it's more like an std array, because it has a compile time maximum upper bound, and it doesn't allocate. So yeah, I think std array is probably the more correct equivalent there on that side. So now we don't need to keep track of the count, because this guy should actually let's see, know how many of those there are. Yeah, len. Right, so we have len here, which is initialized to 0, so that should be fine. Cool. Okay, let's maybe get the render scene. Basis render scene pointer, and we get the tire track renderer. So basis render tire track renderer pointer, and this can just be essentially this init null, and this can just be essentially this. Oh, it doesn't have an init null function. Well, that's annoying. Let's add one to it then. Tire track renderer, we'll just add here init null to this guy. That should really be a self, right? So just this helper method that initializes one of these pointers, these PTRs, with a C++ pointer of 0. That's nicer, and this can really just be self. That's shorter. All of these should be self. There we go. Okay. Okay. Good. And I mean, we could do this. We could do something like this, where we can do render scene PTR and tire track render PTR is basis render tire track render PTR, and now we can get rid of these things here to shorten it a little bit. Maybe it's a bit less heavy on the eyes. Right. So what we need to do here now is do var game object. We can do self context get game object. So that gets the parent game object essentially. Actually, what we do here, maybe we can do this the whole shebang there actually. In which case we don't really need the create even. Basically, what we want to do is we want to assign the render scene is a game object get, or is it maybe it's self context get renderer get primary scene is the one that we want, and tire track renderer is self render scene get the tire track renderer out of the render scene, because each render scene can have their own tire track renderer, so that's just the one that we want to use. That should be good. And right, so now we want to actually start initializing. So we have tire count, right? We can get that out of the vehicle controller, get wheel count. Yeah, like I said, wheel count and tire count, those can be sort of used interchangeably here. So we while with a counter, and we'll count until tire count. And what we will do is, we'll do data is, and it's one of these helper structs that we want to create. So tire state data, use tire state data, and we want to get essentially let's think about this a little bit. So we need the tire track width, and we need the tire track type for these wheels, and we'll probably want to get them from the blueprint property, so that we can select for each vehicle. We can select in here blueprint here in the vehicle blueprints. You can just set here the width and the type of those values in here. But let's just for now let's just add them here, so we can have like tire track width, and we'll set that to maybe half a world unit or something like this, and then tire track type, and that should be just 0, so it just uses the first pattern there in the texture that we looked earlier. Right, so this would be render ID, right? I think so, even though we don't get any IntelliSense currently, but renderer ID, and we'll want to use self.tireTrackRenderer, and we'll want to register the tire. So the width is then tire track width, and here we can again use this I modulo 2 equals something other than 0. And the type is tire track type. So all the wheels of the vehicle will have the same type and width currently. Yeah, so is right side tire, like the tires start with the left side, so index 0 is on the left, and then it alternates between left and right. So all the odd ones will be on the right side. Then we can have a touching terrain. Was it called? What was it called? Yeah, touching terrain. Maybe we'll have that in that order. I think that's perhaps better. Touching terrain, and the default value should probably be false. So that even if it is touching the terrain, we'll start with a value of false, which means that the tick function will then realize that, oh, no, it is touching the terrain. And then start a new one of these tire tracks. So state info dot, wasn't it state info? Yes, and state info has a contact point vector tree. State info contact point is we can use basis. Actually, let's make a shorthand for the vector trees, because I think we'll be using those quite a bit. So vector tree is basis math vector tree. I don't think we necessarily need. Maybe we can have like a math 43. So 4x3 matrix basically, and this should be vector 3. And we initialize it, and we'll do basis math large number, and then just set that to large number, large number, large number. And that should be a comma. But I have something apparently wrong here. Expected field initializer. What's going on? Tire state data. Yeah, I'm very I'm very tired today, so it's sort of like, let's do data 2 just to make sure I don't have that somewhere. And it's not immediately obvious to me what I have wrong here. Maybe some of you are just screaming at me what the problem is currently. Oh, I see. I probably can't actually initialize that, just a part of that, right? So I need to do something like const state info is wheel state info, and do this with like a contact point. Yeah, that's how we want it. And I think all the other fields should be, or essentially all the fields should be initialized there. So yeah, okay, now it builds, or at least now it doesn't complain. Let's do like a quick test build here. We get a bunch of oh, right. I don't want to actually break my game here. I did some bad things. Oh, they're not actually initialized. Well, that's unfortunate. That's unfortunate. Okay. Well, do we really need to like set that up by hand. I guess we kind of do. Well, all right then. Do it like this. Put all of this here, and local transform. We don't have that, so we'll just do like identity there. Contact point we actually had, and all of these should be just 0. Oh, 0. This should be false. No, do 0 and 0. Most of these will actually just be overwritten immediately. So that should be just fine. Surface material CPP pointer is probably just 0. Something like that. See if I actually use this on the C++ side somewhere. Yeah, so the thing we actually use this for, it would seem, is check if the wheel has moved enough since the last tick to warrant any further updates. So the idea of initializing it to this large number here in the beginning, this thing here, is just to make sure that it does get an update immediately when it is created. Movement distance threshold is set to 0.1 wheel units. So we don't update these tire tracks all the time unless they have moved at least a little bit. So that's the idea here. But okay, I think this should probably be fine. Like we don't need to initialize anything else except this contact point, just to make sure that the wheel gets updated immediately. We don't skip any first updates. So now we have the data figured out here. This guy, and with that guy, we can simply push it to the list. So that would be tire state data, right? And then just append the data. And that's probably something that can throw an error or return an error, so we need to try it. Cool. So now we can build. That's nice. Okay, so that's the initialization done. We have a while loop. I typically do these while loops with an added scope here, so that I can just have my I accumulator variable here in its own scope. And then we do while we are less than tire count, we add a new one and we register all the tires with this function here. And maybe now would be a good time to just do the deinitialization. So let's see, unregistered tires. Right, so we have a function here, unregistered tires, which we call in the destroy method. We also call it in the die method. So die is something that is called in slide. Slide features vehicular combat, and you can actually shoot and destroy other vehicles. Not sure that is actually going to happen in Means. Means is more of like a puzzle game. But regardless, if we die in slide, then we unregister the tire as well. I'm not sure we're going to need that, but maybe we'll want to have like an unregistered tires function anyway. So let's add it here. Let's create a private section here. So not pub fn. Unregister tires like this, and then here we have again we have a while loop with a counter, and we can do or actually, maybe we don't need a while loop with a counter, because now we should be able to just do a for loop over. We need a self pointer, self pointer here, right? And for self dot tire state datas and buffer, and we get the tire data, or whatever we want to call it, and that this should be a pointer, like so. And now we can set this to that will be self tire track renderer unregistered tire data renderer ID. That should be fine. And we then want to set this to the invalid tire renderer ID, and we can just have it here as a const as well. So invalid tire renderer ID. This should be 0xFFFFFFFF. So essentially like the largest possible number for a 32-bit integer. And that would be tire. No, not that, but tire data dot renderer ID is that thing. And unregistered tires we need to call here in the self. Like so. Let's see if we can build this. Right, we can't, and that is because we need to actually take the address of the buffer here to be able to do this. Like, I think if we don't need to modify this guy, we can take that away, and if that is the case, I think we can take that away. I'm just going to test this out to make sure I got it correctly. Yeah, this works. But now, if we want to actually change the tire data, then this won't work, because this needs to now be a pointer, a reference, essentially. And if we do that, then we need to take the address of the buffer. Right, like so. So that should be good. Okay, so now we're initializing them, and we are uninitializing or unregistering them. I think the next thing to do is then get the movement direction, because as we looked at earlier, we will need the movement direction for the renderer. And you can see here in the C++ version, actually we can just copy the C++ version over. Let's do that. So C++ version looks like this. I'm gonna indent this once, and then I'm gonna comment it out. So this is what we want to replicate here in Zig. If we have a significant enough horizontal linear velocity, in other words, in the XZ plane, we use that as the movement direction. Otherwise, we use the forward direction of the vehicle. Yes, that looks good, because we need the direction even if the vehicle is not moving anywhere. And the reason we need that is that if we spawn in a bunch of vehicles, we will want to begin their tire tracks, even if they are standing still. And in that case, we want to use just the normal, or the forward vector of the vehicle. They haven't started moving anywhere yet, but to update their tracks, we still need the movement direction, so we might as well just use the forward direction for that. Right, so this should return a vector tree to calculate movement direction, self. This can be just a const pointer, and we'll return a vector 3. And we might as well just copy this comment here. It was a reasonable comment, I think. Like so. So we have self.context transform, get linear velocity. That's how we get the linear velocity in Zig. And we can do linvel xz. Yeah, we can do that. I didn't didn't actually declare a shorthand for the 2D vector, but we can just use it like this. And this would be linvel x, linvel z. Then we can do the same thing here, where linvel x z squared length is bigger than something small. Then we just return linvel normalized, like so. So basically, if the movement is large enough in the horizontal plane, then we use that. And that's fine. Here we actually, we don't use the horizontal horizontal vector as the actual direction, because it wants a 3D vector. But a movement up and down doesn't really make sense to the tire track system. So that's why we use this XZ version here to actually check, do we have a direction that makes sense to the tire track renderer. And then we have context transform get world matrix, and it returns a matrix 4x3. Okay, so we can just do vehicle world transform, and then out of that we can just return vehicle world transform get z, and the z-axis is the forward axis. We're using a left-hand DirectX style, also known as Unity style coordinate system in Basis. Cool. Alright, that is that. Now I think essentially the only thing that we have left to do is implement the tick function. I mean, we still have these two guys here that we can add as blueprint properties if we want to, but let's do the tick function first. That should allow us to actually play around with the system in the game. So ticking should start by getting the state info of the vehicle, I think. Yeah, the C++ version actually does, but then it doesn't really use it for anything. So let's not do that. But let's start by adding these guys here. So movement distance threshold, something like that. Movement distance threshold, this is the thing that we looked at where we don't actually update anything unless we have moved a little bit. Terrain hit distance threshold is related to the raycasting. And, well, we'll get to that in just a second. But basically we'll want to have the same for loop here over this bounded array. So tire data. And here we can immediately, if we somehow get to a tire data that has an invalid renderer ID. So if renderer ID is invalid tire renderer ID, then we just continue. I think that should perhaps never really happen, but it can. So the next thing that we'll want to do is we get the new state info for the wheel, not the vehicle itself, but this particular wheel. So we need to do self.vehicleController get wheel state info. And now we need the wheel index. And so that's kind of interesting. How did this actually work? I think the syntax was something like this, right? So you have a for loop, we iterate over something, then you can do like 0 ... and then you get the index as a second capture here. So that's what we'll want to do. We want to get the tire data, but we also want to get the index So that's a really handy way to actually get both of them in a very concise manner. And actually, does this work? Let's see. Have I done this particular thing somewhere? No, but I think it should work. So if we save and do a test build, it does actually succeed. So that looks good. Right, now we can do. Let's see. We have a comment here on the C++ side. I'm just gonna copy some of these things over verbatim. So distance moved squared. I call it SQ. New state info, contact point, and we subtract it from the tire data. State info, contact point, and then we calculate the squared length. I wonder why we don't get any intelligence, but all right. And then if distance squared is smaller than this movement threshold, and we need to, of course, square that as well to get the proper comparison. You might be wondering why we actually do squared here. Like I could basically do not squared length like this, and then I could compare it like this, and I could remove those things. But the thing with length is that this is significantly heavier than using squared, because we don't need a square root there. So just using squared length and then comparing it to the squared distance, which you just get by multiplying it with itself. This is more performant if you just want to do a comparison. Right, so let's see what happens. What is happening in the C++ version? Okay. Okay, so I do a little bit of a dance here. So we do something like did touch terrain, and that is tire data touching terrain, and then we actually set this thing to false, and if new state info in air is not true, so basically if we are touching something, then we need to do a raycast to see if we are hitting the ground or not. So this is a comment here from C++ version. If the physics report the wheel as not being in the air, do a raycast downwards against the terrain to determine if the wheel is sitting on terrain as opposed to a mesh. Yes, exactly. So we need to figure out how to do a raycast downwards, and we can do it from the render scene. Cast ray. Let's see what we need. We need ray origin, direction, hit group mask, only AABB, and a raycast result. Okay. I think the something like a const terrain. Actually, this is not the const, this is a variable because we will pass it. Terrain raycast result is basis renderer. Render scene, probably raycast result is here, right? And yeah, can we, is this actually init 0 basically? Okay, maybe we can just do this, right? Boom. And so here we have a raycast result that is initialized to 0. And another thing that we will want, we have this raycast hit group, and we want to cast only against the terrain. That's cool. Okay. So if self render scene cast ray, and actually before we do that, maybe we can just have like the ray origin here is, that would be like the new state info contact point, and we'll add a vector 3, which is unit y. So we'll take the contact point of the wheel, we'll move it up 1 world unit. That should be enough to determine or that should be like a pretty good place to start the ray. We're starting it a little bit above the ground, or above the contact point with whatever it is the wheel is sitting on. And the ray direction would then be basically unit y negated. So if unit y points upwards, then we want the ray direction to be downwards. And now we can do self. If self render scene cast ray, we have ray origin, we have ray direction, we have hit group mask, which should then be basis renderer render scene raycast hit group only terrain, and we need to call asInt on it because this thing actually expects an unsigned integer. Only AABB. Sure. Actually, I wonder, is that wise? Is that wise? It probably doesn't matter because we're only raycasting against the terrain anyway. And raycast result, it's this guy that we want to pass, and it wants a pointer, which you can see here. So we'll give it the address of our result, like so. That should be all right. And then I'm gonna copy the C++ stuff in here. After initializer, what is the? I'm just complaining about that. Maybe. No. I probably just needed another closing brace. So if the raycast hit against the terrain is close enough to the wheel contact point reported by the physics engine, we consider the level to sit on the terrain. Right, so now we go back here and we do this whole touching terrain thing again, and we do terrain raycast hit result hit point. We subtract the new state info contact point, and again we do the whole squared length as opposed to length business here. So terrain hit distance threshold times itself, and that should be it. We get some really wide lines here, which I'm not super a fan of, but it is what it is. Okay, so after this whole thing, we should have in did touch terrain. We can just remove that guy. In did touch terrain, we have the information whether or not we touched terrain before, and in touching terrain, we have the information whether or not it is now touching the terrain. And we do initialize this to false straight away, so that if we are in the air. We never actually try to do any of this raycast business or anything. We just set it straight to false. That should be enough. So now we can handle these different cases. We have the thing where we did not touch the terrain, and the state data, it's called tire data here. Touching terrain. So this is the case where we are now touching. So touch down. Then we have the case where we did touch and we are still touching. Still touching. And then we have the case where we did touch, but we are no longer touching. Lift off. Something like this, right? And then finally, what we want to do is, actually it should be inside the for loop. Let's put it in the correct place. So tire data dot, and this would be, let's see. State info and new state info. So we set the new state info, which we got here from the vehicle controller. We update the tire data with that information. Cool. And now we just need to actually begin, end, and update these tire tracks. And I did mention previously that we were unnecessarily calculating the movement direction for each and every wheel, even though it will be the same for every wheel of the vehicle. So we can just calculate it here. So we can do movement direction, and that was just called self, that calculate movement direction. Right. So touchdown. We have now started touching the ground. We will want to begin a tire track. So tire track renderer, begin tire track. The ID is tire data renderer ID. And then we immediately want to update. No, tire track renderer like this, and update tire track. And that is the same ID again. So tire data renderer ID. Contact position will be new state info dot contact point. The movement direction is simply movement direction that we calculated. We have new state info dot longitudinal slip. We have new state info dot lateral slip. And I think the normal was the last one that they wanted. So this would be the terrain raycast result dot hit point normal. And we can add a comma after that and save, and it will format it for us vertically instead, like so. So this thing. And that is basically the only thing we want to do if we are still touching. And if we are lifting off, so to speak, the thing we want to do is ending. So tire track renderer, end tire track. And it's still the tire data.renderer ID. That doesn't mean that the tire track will be removed from the world. It will fade away with time. That's something that the tire track renderer handles for you internally. So that should look quite nice. Let's try to build this now. And as it is building, we can get this registration name here, and we can just add it to the test vehicle. So this guy, component type is tire track component. We can just call it tire track. It will complain that it's not a registered component type. Maybe we'll still actually register that in this video if we want to actually adjust those settings. We only need it on the client, so we can untick server and save the blueprint. And in the meantime, this succeeded, so now we can actually just test this out and see if it works. And would you look at that? We have tire tracks, and we can see here that we have the variant here with the perfect grip going on. Now if I use the handbrake, make some handbrake turns here, for example, you should see that this starts to be more sort of faded. It's not super visible here currently, but the place where there's actual slipping with the wheels, you get this more sort of smudged version of this. It can be a little difficult to spot sometimes. Let's see if I can demonstrate it a bit further. Here you can clearly see that there's like one which is very sort of smudged, and then we have this other one which has this more distinct pattern. And now if we just let this guy continue, we should see that over time these time tracks start to fade away. Now we can almost not see them anymore. And now we simply have this thing here. So what if we get a little bit of air time going here? So you could see there that we actually got this portion here without any tire tracks. All right, cool. Well, this basically works. I'm sure there's a little bit of adjusting maybe to be done, but it basically works. And is this? Yeah, this cliff doesn't have the correct physics settings set, so you can't actually drive on it currently. I need to fix that. All right, so we got an assert here. The tire is in use, unregistered tire. Okay, I wonder what that is about. Let's see if we can actually find this here. So add like in use and search for that. Tire track manager. Oh, tire track renderer, sorry. So what is that assert about? Unregistered tire is in use. So apparently that tire was not in use. It should have been in use. So that's an interesting thing. I'm pretty sure that's something that we shouldn't have to really mess around with ourselves. Oh, I think I might actually know what the problem is here. We're unregistering the tires, and we're doing it with the buffer, and the buffer has a capacity. Yeah, so let's see. Yeah, there's a slice here. View the internal array as a slice whose size was previously set. So we don't want to. Actually, we don't want to iterate over the entire thing. We only want to iterate over the ones that we actually did push, right? So 0 to self length, yeah. Yeah, this is confusing because this is like the return type of the function. The return type is, well, actually that. The return type is a whole switch sort of expression, which made me not really understand it at first. But yes, so it returns a type depending on what kind of buffer you're actually dealing with here. But regardless, the return type is still this expression here. So it is a slice, right? Good, and that would mean that we would do something like slice like this instead, right? Then I think now we don't need that, and we'll want to do the same here as well. So that would be take the address off away and return slice like this instead. And let's see, does that build? It builds in debug. Let's build it in release. And of course, the reason why we didn't go into just like garbage memory here is that we have this if check here, which is needed in the C++ version because this is just a raw array. But I don't think we need it here in the SIG version now that we're using the slice rather than the raw buffer. So small differences between SIG and C++, but I think I like SIG better in these cases where you actually have nice native slices. Now we should be able to just close this without it breaking, and we can. So that's nice. All right, cool. Okay, so maybe we should still actually put these things into data. That would be kind of interesting. And that would mean actually adding a blueprint properties object. Let's see, did I have any blueprint properties objects here in means? I have some in the VHL library at least. Here we have debug object component. This has some blueprint properties. All right, cool. Props. Right, yes, okay. So blueprint properties works like this. You basically define a small type, like a struct, and it needs to have a load JSON public function, which takes some JSON data as a string and initializes this thing with all of its property members. Essentially, this thing just has this boolean set as avatar, and then once you have this guy created, you simply add an optional pointer or const pointer to one of these guys. You initialize it to null. This thing gets automatically set for you based on the data that you set in the asset browser. So let's add all of this. You have the context there, and we can just copy this line, set it next to context, and we can call it something like tire track components, tire track component blueprint properties, and we add those here below. So tire track component properties, that would be like std mem allocator, I guess. Do we actually need the allocator? Yes, we do, because we pass it to the std JSON parsing library. And I typically use like a small inline struct here in the load JSON to actually parse these things, so that if I want to change the data, I don't actually have to change the layout of this blueprint properties object all that much, or at all, ideally. But basically what we want to do is this. We have these two guys. We want to set them through data. So tire track width, that should be a float, so F32, and we can initialize it to 0.5, just to have something there. Tire track type, this is a U32, and we initialize it to 0. Take those guys away. And then we basically want to, in this case, not always, but in this case, we want to have these two things here as well. And we want to simply copy them over. And this might seem like a little strange. Like why would we actually want to have these things sort of duplicated all over the place? The reason is that you might want to have an enum, for example, which has a bunch of different values. You might want to have them as strings in the JSON data, but actual enums here in this component properties type. So that would mean that you would have like some enum here, and this could be some enum type or something. But in here you would actually have it as like a const U8, so basically a string type. And then you can do a little bit of conversion yourself. You don't have to do it that way. You can still actually just get it as an enum and still have it as a string type in the data. And you can have it automatically convert from strings to enums, etc. But if you want to have full control over that and be able to manage how the data is updated, etc., etc., it's kind of nice just to have an internal props object here, which has the exact layout that you expect, and then do the conversion yourself. So this is how I do it currently. Okay, and now then, where is the part we want to change? It is right here. We can assert here, basis assert, that we have self dot, okay, something is unhappy. Is it just the fact that I took those away? No, there's something else that is unhappy. Let's try to build this and see if we get some kind of error. Sometimes the Zeek language server is just like really doesn't want to be your friend for some reason. This seems to be one of those cases, because it takes long enough that it actually did succeed. Yes. So self, yeah, like it doesn't want to give me anything here. But here we have blueprint properties. Like I don't understand why sometimes it won't give me those things. But anyway, let's just assert here that we actually have blueprint properties. Const is bp props, and since that's an optional, we can get it out of the optional type like this with a dot question mark. Before that, you should somehow make sure that you actually have those. In this case, I just assert that they are there. That means that I get a nice assert failure screen, similar to how we got earlier with the in-use stuff. And yeah, that's that. So tire track width, this would be tire track width, tire track type, like so. And I think this is the only thing we need to do currently for this thing. And now we need to actually somehow add the UI there to the asset browser. And we can do that by, maybe we can actually, the easiest way is just to go here, and we can explore to this, to the blueprint, and go here, and we go to work folder root, we go to metadata, component UI definitions, and we can look at these things. So here we have a type, means.debug object component, and this is some information about the component itself. We can suggest a name for it, and we can set here whether or not it supports client server level editor and asset browser. And then it has just this one checkbox set as avatar here. That's actually pretty good. Let's just use that. So let's copy it and rename it tire track component, and tire track component, tire track. It supports the client, yes. It doesn't support the server or the level editor or the asset browser. Makes no sense to have it there. So here we can have this called something like, let's make sure we get the names correct here. The names in the JSON data, so essentially this thing that we are interested in. So time track width, its type is, and now I should really remember how this works, but I think it's just float. Default would be 0.5. The display name is tire track width. We should, I guess, put in a description, so the width of the tire track, kind of obvious, but still. Explicit default value, so this basically means that if you have this to false, or you just leave this out, if this is set to 0.5, then it just leaves it out of the data. It kind of expects that, yes, it is not set, so just use the default value. We probably just want it here anyway, so we'll leave it at true. Then we have the other thing, which is type, tire track type, and that would be tire track type. And this thing in the JSON name, this should match this guy here. The type of the tire track type, an index into the list of patterns available, something like that. Default is 0. I don't actually remember what that should be. It shouldn't be float. It should be integer 32. Let's see if I can actually find out how I actually listed that. That's why I'm going through this to see if I have. It's probably like maybe types, right? Vec3, no, you can have enums, you can have all kinds of things. Alright, so this doesn't really help us all that much. I'm going to go into slide, which has lots of these guys. So work folder root, metadata, UI defs. And here we have just lots and lots of these things. So something like this maybe. Vector3, resource mesh, string float, bool float, uint32. So that's how you actually, that is how you set that thing. Auto gearbox, debug component. Apparently we somehow managed to lose track of our tire track component, so copy it in there. uint32, default 0, display name, tire track type. And that should be basically exactly what we need. Cool. So let's actually delete this now, so that we will add it back using the proper proper way. So reload component UI definitions. Now we can go to test vehicle. We can add a component. And now if we type tire, it will actually suggest the tire track component. We add OK. And we can see that now we can no longer create server level editor or asset browser preview because we set it to not support those. We can't actually. It doesn't make sense to have tire tracks on the server. It's a purely visual thing. We didn't have to set the name. It suggested tire track, and it sets these two things for us. So that's pretty cool. Now if we save this, and explore to this guy, and in the diff, we can see that you get these properties created for us automatically. Don't have to write any manual JSON there. And this, meanwhile, has built successfully, so that's fine. And now we should be able to try this out, and we see that yes, we do have tire tracks. If we set this to something ridiculous like 3 times as wide, we should get 3 times as wide tire tracks, which we do. So it does work. Okay. That's nice. Set it back to half. Cool. It's a small detail, and it doesn't really look all that good when we have this checkerboard default texture, but it's a pretty nice effect, and it looks really bad when you actually start adding more detail to the scene if your vehicles don't have any kind of tire tracks or marks that they leave behind. So this is nice. I've been meaning to do this for a while now, but I just haven't gotten around to it. So this got a little bit rambly. It's a little bit of a slow day for me today, but it was a pretty good day to do something laid back and not that complex. I hope this was at least a little bit interesting to you. This was a pretty good example of what it's like to take a piece of C++ code in Basis and rewrite it using Zig. It's not super different after all. The languages do support a lot of the same concepts, and the game component system works pretty much the same way on both Zig and C++, at least conceptually. So it's just a question of changing the C++ functionality into Zig. Anyway, I hope this was fun. I hope to see you in a future video. If you have any questions or comments, write them below. Like the video, subscribe to the channel, do all the things that you're supposed to do. I appreciate it a lot, and I hope to see you in the next one. Bye.